Good morning, everyone. I am Jaegyoon Hahm, Director of the Center for Quantum Computing Service at KISTI. It is my honor to share our recent national strategies in advanced computing with you. Today, I would like to talk about strengthening national competitiveness through advanced computing. My focus is on how HPC, quantum computing, and AI can be connected to as one national capability for science, innovation, and future growth. Let me begin with why advanced computing matters now. Advanced computing is no longer just a support tool for research. It is becoming a core national capability for science, industry, and innovation. In this convergence flow, HPC provides scalable computing power and quantum as next-generation computational capability. Together, they accelerate AI. And once AI becomes more capable, it enables faster and deeper scientific discovery. So the real message is simple. HPC and quantum powers AI, and AI amplifies scientific discovery. With that overall logic in mind, let me first walk through the national HPC track. The Korean national HPC system already has a relatively mature institutional foundation. It is supported by law, a 5-year master planning process, and the governance structure for national coordination. This means HPC is not treated as a one-time infrastructure project. It is managed as a national strategic capability with long-term planning, coordinated investment, and structured implementation. The key policy objectives are clear: expanding infrastructure, achieving technological sovereignty, and broadening the application of technology across research and industry. So, HPC already functions as the operational backbone of advanced computing. Let me now move from the framework to one of the most visible outcomes of that policy. One of the most important national HPC initiative is KISTI's supercomputer number 6, which is referred to as Hangang. It is scheduled to begin operation in the third quarter of 2026 with 600 petaflops of performance, large-scale storage, and high-speed networking. But the real significance is not only scale. It is the shift from a CPU-centered system to a GPU-centered, AI-ready infrastructure. This means the national computing platform is evolving to support not only computational simulation, but also data-intensive science and modern AI workloads. Infrastructure scale is one part of the story. The next part is how national HPC resources are organized and shared. The national HPC system is organized as a two-tier structure. At the top is the national center, which serves as the hub for resource coordination, integrated operation, strategic planning, and the management of a common resource pool. Below that are specialized centers, which provides domain-focused infrastructure, technical services, and user support in major application areas. The key point is that these two tiers are connected through shared resources and joint utilization. This allows centralized coordination and field-level specialization to work together more effectively. So far, this is overall picture on the HP side. policy foundation, flagship infrastructure, and operating structure. Now, let me pivot to the quantum side, starting in the same way with the policy and governance foundation. Quantum computing is developing within a rapid expanding national policy framework. It now has a dedicated legal basis, a comprehensive national plan, and a high-level governance structure. What matters here is that quantum is no longer seen only as a future research topic. It is being positioned as a strategic national field linked to industrial competitiveness, talent development, supply chains, and long-term technology leadership. So, this slide gives us the policy foundation for national quantum development. The next question then is what this framework translates into a broader strategy. This slide shows what the national quantum framework translated into in practice. The strategy can be summarized in 4 directions. First, the development of a K-quantum computer. Second, the expansion of quantum plus AI use cases. Third, the development of hybrid infrastructure connecting quantum computing, HPC, and AI. And fourth, the formation of regional quantum clusters. Together, this direction shows that the national quantum agenda is not limited to research alone. It is designed to support technology development, industrialization, and ecosystem building in parallel. So far, we've seen the HPC track and quantum track. Now I'd like to move into the layer that starts to connect them more directly. That connecting layer is K-Moonshot. K-Moonshot is a national initiative designed to integrate AI more deeply into science and technology, and to link computing resources with mission-oriented national priorities. In that sense, it works as a bridge between broad strategy and practical execution. It reframes advanced computing as more than infrastructure. It becomes a platform for solving national challenges and for improving research productivity at scale. So, after seeing the separate HPC and quantum track, K-Moonshot helps show how convergence can be turned into action. This brings me directly to KISTI's role in implementing that convergence. KISTI is expanding its role from an HPC operator to an HPC quantum AI convergence hub. It is leading national efforts in quantum services and utilization systems, including introduction of an IonQ system. At the same time, KISTI is developing hybrid platform that links quantum systems with the supercomputer number 6. This is important because the future of quantum computing will depend not only on hardware itself, but on how effectively it is integrated with classical HPC and AI-enabled workflows. KISTI is also supporting this ecosystem through education, workshops, hackathons, and user services. So the goal is both infrastructure and practical utilizations. Let me now summarize the entire story in one final framework. These slides summarize the core logic of the entire presentation. HPC provides scalable computing power, quantum computing as next generation capability. Together, HPC and quantum accelerate AI. Once AI is accelerated, it enables faster, deeper, and more effective scientific discovery. So the value of convergence is not simply that different technologies are connected. The real value that convergence creates a pathway from advanced computing capability to scientific breakthroughs. This is why central message of this presentation is convergence for scientific discovery. National competitiveness will increasingly depend on how well we connect infrastructure, emerging computing paradigms, AI, and scientific outcomes into one coherent system. With that, let me conclude. In conclusion, advanced computing should be understood as an integrated national capability. HPC and quantum can accelerate AI, and AI can amplify scientific discovery and innovation. That, I believe, is a core direction for strengthening national competitiveness through advanced computing. Thank you very much for your attention. I would be happy to take your questions.